okay, they all travel at the same speed, okay? I think here in a minute we're going to, or probably on Wednesday, we'll be talking about Einstein's E is equal to mc squared. The variable c in E is equal to mc squared actually is the speed of light in a vacuum. Now when they say speed of light, they're actually talking about one of a set of energies called electromagnetic radiation. So all of these things travel through space, as long as it's a vacuum, at the speed of light. The other thing is that they travel in little packets of energy called photons. When we talk about in Chapter 4, when we talk about telescopes, we're going to actually see one thing to call telescopes is like a photon bucket, little tiny light energy packets of energy, okay? So all of these different forms of electromagnetic radiation, they all travel at the speed of light, and they have both a wave aspect to them and also a particulate aspect. So gamma rays, X-rays, ultraviolet, of course ultraviolet is UV, infrared is IR, okay, microwaves and radio waves. As I have them listed, I bet you would say that gamma rays are the highest energy, E for energy, and you would be right. Radio waves have the least or lowest energy. So we could actually, if we were to see light traveling or any form of electromagnetic radiation traveling through space, an aspect that's very important is what we call the wavelength. Okay, so those cousins, the gamma rays versus the radio waves, they differ by their wavelengths. And so in order to understand wavelength, we have kind of a visible wave that you can see. Wavelengths are from crest to crest or from trough to trough, okay, how long that wave is. Notice here we have the speed of light in the metric scale is 300,000 kilometers per second. So we use the variable lambda for the wavelength. So lambda is like an upside down V with kind of a little caret on it. That's the Greek sign lambda, and that means actually distance, okay? So one of the things we're going to see is gamma rays are very energetic, and they have a short wavelength. Radio waves are not so energetic, and they have a long wavelength. Frequency is also important, and actually, if you know the wavelength, you automatically know the frequency. And if you know the frequency, you automatically know the wavelength for these energies. Frequency is basically, I tell students, if you are standing put and you have a counter, okay, and you have 1 second on your, you have a counter and a timer, you set your timer for 1 second and you count the number of cycles that pass you. Okay, so it's cycles per second. That's what frequency is. And some of you may be familiar with the term hertz already. Hertz is cycles per second. So frequency of these energies is going to be in hertz. Okay. So the fact that they all travel at the speed of light has this cool thing going on for all of these different energies. Okay. For any energy, okay, we can take their wavelength times their frequency for any energy, okay, and that will be equal to the speed of light. For waves that travel at varying speeds, we could say velocity is equal to the wavelength times frequency. But for these things, they all travel at the speed of light. So the speed of light is equal to wavelength times frequency for any of them. So in a minute, actually, that's a player. If I focus on that aspect of it, can you see where as the wavelength decreases, and I'll put a down arrow, as the wavelength decreases, okay, notice that the frequency is going to have to increase because multiplied by each other, it's a constant. Okay? So I like this figure. And it's kind of a busy figure, but it kind of takes it. We end actually finally with astronomy, how electromagnetic radiation relates to astronomy. But here you can kind of see the cousins at the top there. Okay, you see gamma rays, X-rays, ultraviolet rays, And here finally you see where visible light fits in. We'll call that number 4. Okay, longer wavelength than that, number 5, infrared. Radio waves, actually microwaves are before radio waves, 6, and radio waves are 7. So here we have some everyday common objects that are kind of similar wavelengths. Okay, a hydrogen atom is very small, but as far as a repeating unit of an X-ray, that's about the distance between crests for X-ray electromagnetic radiation waves. Going up to something a little bit, okay, light, tends to be in the ballpark of the size of a bacterium. Okay, if we're up to microwaves or radio waves, now you're talking about the repeating unit being about the size of a baseball. Then it's like a logarithmic scale, okay? Football field has to be about the size then of what the radio waves are. So like we said a minute ago, the wavelengths for the high energy are short wavelengths, for the low energy are long wavelengths, okay? So we said that as wavelength, we'll start over here at the radio waves. The longer wavelengths, we must have shorter frequencies, and that's exactly what we have. Longer wavelengths, shorter frequencies. Okay, shorter wavelengths, higher frequencies. And just so we're all on the same page, I think I did talk about scientific notation a little bit. This 10 to the 20th means that if you were standing still, you would have 1 times 10, oh wait, sorry. You would have 1 and then 20 zeros, 1, 2, 3, 4. So in 1 second, that's the number of cycles that pass a point. That's cycles per second. That's a lot. Okay. 10 raised to the 6th, of course, is 1 million, and that's a lot, but that's a lot. So then relating to everyday objects here on Earth, okay, radioactive elements will emit the gamma rays or X-rays. X-rays, of course, machines work in the X-ray region of energies. Light bulbs emit visible light. People ooze infrared radiation. One of the things in astronomy is we look at a lot of heat signatures. So actually, anytime you see IR, that is the same thing as heat. So that's what these folks are oozing. I always think of like if you're a hunter, or if you're looking for somebody that's trying to hide from you and it's dark, okay, you can actually thermally find where they are. They are oozing information. Here on Earth, we dabble in radio waves using radar, microwave ovens, okay. So that's all well and good here on Earth, but we're taking astronomy, so why would we care about these energies coming from celestial objects? So down here along the bottom, I actually kind of tell you it for each cousin, for each form of energy, why you would care. So this idea of gamma ray bursts, usually people come to this class intrigued by the idea of black holes and that sort of thing. So actually that is associated with black hole activity. We can actually see black holes. I know you can't really see black holes, but we can infer the presence by looking for X-rays. Of course, we study the sun in all sorts of different wavelengths. Okay, I said that we look for objects oozing infrared in the sky. This actually, the cosmic microwave background is the hiss at the beginning. I'll just put BB for Big Bang here. Radio galaxies, being able to understand them, the energies they are sending in long wavelengths. Now, in Chapter 4, near the end of Chapter 4, we're going to talk about different telescopes. And the telescopes we're going to use this semester actually gather light information. But there are other telescopes out there that are geared toward gathering other different types of electromagnetic radiation. So wavelength and frequency go together. As one goes up, the other goes down. As one goes down, the other goes up. And actually, this slide talks you through 3 different waves and kind of how that would look. These are all electromagnetic radiations, so they're all traveling at the speed of light. So for instance, this one, we have a wavelength of 1 centimeter, which is about like that, okay? Frequency of 30 gigahertz. So the term giga actually means 1 billion. So now, here's the deal. If we go ahead, we'll call that wave A. We'll call this wave B. If we go ahead and cut the wavelength in half, so now it's not 1 centimeter, but it's a half a centimeter, notice what that does to the frequency is it doubles the frequency. Okay? So those two remain the same. It's always going to be that for any electromagnetic radiation, if you take its wavelength times its frequency, you'll always get the speed of light. And then we'll call this C. So for one other one, then we're going to take the wave A and actually make it a fourth of the wavelength. So instead of being a whole centimeter, it's a quarter of a centimeter. Notice what this does to the frequency. It bumps it up times 4. So instead of having 30 gigahertz, we have 30 gigahertz times 4. The frequency now is 120 gigahertz. So that's kind of how that works. So just to kind of reinforce, you know, as we have, we shorten, this red line is actually showing the trend in shortening the wavelength, and it's increasing the frequency. And actually shortening the wavelength would increase the energy of the photons too. But for any electromagnetic radiation, if you take its wavelength times its frequency, again, you'll get the speed of light, which is kind of fun. So one of the things that Newton did, among lots of different things, was he used a prism to actually separate white light from the sun into colors of the rainbow. Now, you're going to want to probably orient yourself as to colors of the rainbow. And he came up with actually 7 colors of the rainbow. I don't know about you, but I've never heard a young kid say, hey, pass me that indigo crayon, right? Pass me that red crayon, that orange crayon, that green crayon. Actually, I heard historically he introduced a 7th color, indigo, between violet and blue because he didn't want 6. So a good way to remember those, if you haven't already run into it before, is the mnemonic device like a name, Roy G. Biv. And if we go that route, then red is the longest wavelength of visible light, and violet is the shortest wavelength. Okay, so red is the longest. And you're going to want to be able to understand that this symbol is wavelength. So red is the longest wavelength, and violet is the shortest. One of the things I tell students I think is kind of cool is that if we look at the cousins we saw on the slide a few slides ago that kind of had all different forms of electromagnetic radiation, starting with gamma and ending with radio, notice that kind of in the middle there we had UV, ultraviolet, and then we had visible, and then we had IR. For this is going longer wavelength, and this is shorter. I mention that because now if we want to go ahead and plop in our Roy G. Biv, actually it's going to be going backwards. It goes like this: red, orange, yellow, green, blue, indigo, and violet. And I love things, I don't like memorizing things in science, but I love things that kind of connect like this. Do you see where violet, the color violet, actually kind of connects up with ultraviolet radiation? And the color red actually bumps up against infrared radiation or thermal energy, heat. So I know this isn't a chemistry class, but in order to kind of understand, explain how scientists understand information they're getting from stars and such, we need to understand kind of the basics of matter. Okay, so we need to kind of dive into what is up with an atom. So as you probably know, all matter is made up of atoms. Sometimes those atoms join together to make chemicals. Sometimes they're just regular old atoms. But the structure of an atom you may have learned before, and you kind of need to know in here. The structure of an atom has kind of a hard, chewy center called a nucleus. Okay, and in the nucleus, just like this slide shows you, in the nucleus actually we end up with 2 particles. Okay, so over here, this is the nucleus, Okay, and the two particles are actually protons. We use the symbol plus for protons. Okay, notice two colors in there. And neutrons. We use the symbol circle for, as in no charge, free for neutrons. Okay, so in the nucleus we have protons and neutrons. And of course you kind of see from, and this usually makes me itch, you see kind of this, that actually is the electron cloud. It's not to say that each particle there's really that many electrons. It's actually to say that we really don't know where the electron's going to be. It's just going to be, we know the general region it's going to be, and it kind of gets down to calculus and probability. But actually, so those are the electrons. The symbol for an electron is the little negative sign because they are actually electrically charged. A cool thing about the way an atom is set up is that you notice protons are positively charged, electrons are negatively charged, but they're equal magnitude. So if you have a neutral, and we're going to talk about ions just briefly, is if you have a neutral atom, then you're going to have the same number of protons in the nucleus as you do electrons in a cloud outside the nucleus. So that's an atom. They are very small. An atom is mostly made up of empty space because those electrons, okay? So that's kind of an atom. So when we talk about atoms, there are various properties of an atom you need to be able to kind of intelligibly talk about, actually even in astronomy. When we say that, we've already said in this class that stars are great at taking light elements and making heavier elements out of them. So kind of along those lines, what they are doing is increasing what we call the atomic number of the atom, the nucleus of the atom. Atomic number means that you have actually looked in the nucleus of an atom and counted protons. It's wonderful. Okay? Notice that, and I didn't mention this, but it's on the slide. Up here, with regard to protons, what's so important about them? It's very important. Protons are awesome in the nucleus, telling you what sort of element an atom is. So we actually, this semester, have a periodic table in this room. It just kind of works out that way. On the periodic table, notice, and they're red, there's a whole red number in the box for the elements. You probably recognize, K for potassium, Ca for calcium, H for hydrogen. So those boxes have a red number. That red number is the number of protons in a nucleus of an atom, or that sort of element. And it's kind of arranged. It goes across a row, and then it goes to the next row, and then it goes to the next row. So that's what we call the atomic number for that element, the number of protons in the nucleus of an atom of that type of element. There actually is another thing that fully kind of rounds the description of, well, not fully, but more information about an atom is actually its mass number coming up. It's atomic mass number. Now, I learned it just simply mass number, but your textbook used atomic mass number, so it's the same thing, so hopefully you'll bear with me. But the mass number looks at the nucleus, you count protons, you count neutrons, okay, and whatever count you get, that's the mass number. So it's got to be a whole number because you can't have a part of a proton or part of a neutron. So mass number is counting those particles. I think probably the reason they call it a mass number is when an atom is an atom, the three particles we talked about, it's only the neutrons and the protons that really bring any appreciable mass to the atom. So the last thing is then the ion thing before we leave this slide. So ions, I said a minute ago, a lot of atoms, just regular old atoms as you're walking around, are equal. That's to say that the plus charges in the nucleus are the same as the minus charges of the electrons. Most of them are equal. Let's pick on carbon, for instance. And actually I have a slide coming up about carbon. But if you look at carbon, okay, it is atomic number 6. Okay, so that means if we look at the nucleus of a carbon atom, it is going to have 6 protons. Okay, 6 protons. So if it's neutral, then it's going to have 6 electrons. Okay. I don't think I'll pick on hydrogen because hydrogen gets kind of complicated. Let's pick on iron. Iron, if you look on your periodic table, any periodic table, of course the symbol for iron is Fe. It's atomic number 26. So if we look in the center of an iron atom, this is the nucleus of an iron atom, it's going to have 26 protons. And it's going to have some neutrons. Neutrons are important, otherwise those little protons wouldn't like to coexist in the nucleus by themselves. But if it's neutral, iron is going to, of course, have 26 electrons. Okay? That actually will be neutral. Now, iron's a good example because iron tends to form an assortment of charges, including a +2 and a +3 ion. Okay, so this is a neutral atom. Okay, if we go ahead and kick off, check this out. I'm going to kick off 2 electrons. 2 electrons are going to go away. So now I'm going to write my iron. I still have 26 protons in the nucleus. 26 protons. Okay, and now in the electron cloud, instead of 26, I have 24 electrons. Oops, -2. 24 electrons in this cloud out here. Okay, so now I don't have an equal charge. So that's why this iron right here that I've drawn here actually is running around with what we call an Fe2+. It's running around with a +2 charge. Okay, so that's how that works. I think I got this right. The problem, though, in astronomy, for whatever reason, if you're a chemist person, for whatever reason, what astronomy would do is basically take the charge +1 and make it Roman numerals. So I'm sorry to say that actually in astronomy they would call this iron 3. Don't blame me, okay? All right, so that's ions. Okay, now there's actually an important thing that can happen with the neutrons. So you figure the protons and the electrons make it neutral or charged. Okay, the neutrons actually make it heavier or lighter. So remember, neutrons are just kind of embedded in the nucleus with the protons. The thing is some elements can have different, what we call isotopic forms. They can have different number of neutrons in their nuclei. So here we have 3 versions of carbon. Notice in each of these versions of carbon, if we call them carbon A, carbon B, and carbon C, notice they all have 6 protons. Okay, but in carbon A, it has 6 neutrons. So under there, I'm going to put 6 + 6. I'm going to put the mass number of 12. Call this one A, B, and C. They all have the same number of protons, but the mass number, or atomic mass number, here it's 6 + 6, 12. Okay? Catch up with me. Here, it's 6 + 7, 13. That's the mass number. Here we have 6 + 8, so a mass number of 14. They're all carbon atoms because they have 6 protons in their nucleus. Let's go ahead and say they have 6 electrons, so they're neutral. Okay? But of course, the carbon-14 is heavier than the carbon-12. Actually, as it turns out, carbon-14 is pretty darn, I'm going to go ahead and say rare. If you've ever heard of carbon-14 dating of objects, it's a way to use the fact that when we are alive and we are interacting with the atmosphere, we are adding carbon-14 to our bodies that are actually, we're adding this particular isotopic form of carbon-14. When we die, okay, no more carbon-14 is going to be added. The thing about carbon-14, it's rare. Part of the reason it's rare is because it's relatively unstable. Once we, okay, or if a plant dies or whatever, okay, ceases to interact with the atmosphere, then basically the clock starts ticking, and whatever carbon-14 they added to their bodies while they were alive starts decaying. So basically what they do is they dig up the body. No. They look at that organic matter that used to be alive, and they look at how much carbon-14 is left. The less carbon-14 is left, the older it is. So that's kind of how they do carbon-14 dating. Okay, so those are different isotopic forms of carbon. Okay. This actually, the hydrogen, helium, and carbon, those are obviously different elements, okay, and that has nothing necessarily to do with isotopes. but your author's done a good job in kind of saying, I like the pictures. I'm a picture person. Okay, so here we have actually hydrogen. Now, whenever you see kind of a shorthand notation like this number up here in the upper left-hand corner actually is its mass number, or atomic mass number. Okay, so what they're saying is it has an atomic mass number, a mass number of 1. All right, well, if it's hydrogen, it's got to have 1 proton in its nucleus. So that means it has 0 neutrons, and that's exactly it. Okay, normal hydrogen has 0 neutrons. Okay, here we have helium. Symbol for helium is H, uppercase H, lowercase e. Okay, it's actually on the periodic table has the large red number 2. So that means it has 2 protons in its nucleus. And the most normal form of helium actually has 2 neutrons. So 2 plus 2 is 4. Okay, neutral 2 electrons. So that's kind of how that works. All right. So I'm almost done with the, well, I should say, not quite. Almost done with the chemistry stuff, but I am amazed that, well, first off, if you think of water, water is 2 hydrogens, I'll put this whole thing up here, and 1 oxygen. Okay, have you ever thought about water? Okay, so here we have an oxygen atom, here we have a hydrogen atom, another hydrogen atom. Okay, these right here are actually what we call chemical bonds. And you're like, dude, why do 2 hydrogens and 1 oxygen want to get together like that? And it's just a favorable situation. That's why compounds like water form. Okay. The other thing, and this slide says it, I believe, is whenever you form those red dashes or chemical bonds, whenever you form a chemical bond, actually the reason they are forming has to do with the electrons. I mentioned favorable. Not only is it favorable, but it's electrons either kind of jumping ship, okay, or being shared between the 2 atoms that the chemical bond is between. Okay, so I am, like I said, kind of amazed. Not these compounds necessarily, but things that we see in outer space. So, for instance, we can study, of course, CO stands for carbon monoxide. Okay, kind of the stuff that's deadly if you have, it can be deadly, right? But in outer space, they can actually detect the presence of carbon monoxide in radio frequencies. Is that not cool or what? Like the molecule carbon monoxide. Aside from that, just think of actually in the next chapter, we're going to talk about the formation of our solar system. Think of here on Earth, we've got liquid water, solid water, gaseous water here on Earth. Those molecules were able to form and ultimately be a part of our planet. I just think that's amazing. All right. So, the reason we talked about, it's coming up, atoms. We don't need to know about atoms about this part. When I talk about light, what I'd like you guys for the semester to think of is kind of think broadly. I'm going to just say light is actually, I'm going to put gamma rays, gamma to radio. Okay, all different forms of energies. So when different forms of energy interact with atoms or matter, we have a couple of outcomes. Okay, that light can be emitted from the object. The object can absorb light. The object can transmit light. Okay, and the object or the object can reflect or scatter light. Okay, now what happens when light meets matter depends upon what light it is and what matter it is. Not so surprising. Okay. Light bulb is an example of emission. We're going to talk about colors here in a minute, but you guys know that on the hot, sunny summer days, when the sun's out and you want to be as cool as possible, you wear white. You avoid wearing black. So the reason is that when you wear a black shirt, actually that's a good example of absorption with regard to colors of light. Okay, the reason something appears black is basically it's not reflecting any colors. It's absorbing all colors of light. An example of transmission would be a window. Oops. Go. Okay. What does the as we look outside and see the sun, see any object outside, we are basically, light is allowed to go past our glass. Okay. An example of reflection would be a mirror, or the example I have here is that light scattering, when you see the reflection of the sun in a river or a pond, okay, that light is being reflected or scattered. So, I mentioned black. If you don't wear black, because basically it absorbs all colors, that absorbs Roy G. Biv. If you're wearing white, that's a better choice if it's a hot day and the sun is shining. Okay, because white actually is reflecting all colors of the rainbow. It's amazing that actually all colors, like a piece of paper that's white, all colors are being reflected from that, and they're being remixed, and then we perceive them as white. I just think that is so cool. Okay, nothing is being absorbed. So we could consider actually this really busy slide where we have the sun actually is shining in all directions. It's shining more than just visible light. It's got the whole other forms of energy. Thank goodness that the Earth's atmosphere blocks a lot of energies, harmful energies from the sun. But the example here, for instance, if you look at the tree, okay, basically all colors of light shine on the tree, and this is where I like to bring in the Roy G. Biv, the colors of the rainbow. Okay, red, orange, yellow, green, blue, indigo, violet. They strike the tree, okay, and green, okay, is reflected or scattered, and then everything else is absorbed. So absorbed would be the red, orange, yellow, blue, indigo, violet. Okay, so like the Roy Biv is absorbed, the green is scattered or reflected. So that's kind of how that goes. All right. So we'll kind of introduce you to this, but I don't think we'll get all the way through it. So when we talked about the structure of an atom, we said that electrons, okay, thank you. Electrons are in a cloud outside the nucleus. And one of the important things about electrons is that they're in a, well, let's just wait. Let's hold this topic because it's all kind of a packet. And I'm afraid if I introduce this, we're going to forget what we talked about on Wednesday. Actually, I have some prompts to bring too. So we'll start here on Wednesday. What's that?